You're watching my video on pressure and how pressure affects fluid. We will be defining fluid and describing how to calculate it as well as its uses in daily life. So we're going to start with the definition of pressure. Pressure is when force is applied to an area, right? So if we look at this block of wood, I guess, applying a force on this surface, well, the amount of force being applied is the force, naturally, and the area is the area this block of wood covers. So this, right, because it's the same on the other side, because it's a prism. This on the other side is the area that the force is being applied. No force is being applied here or here. It's being applied directly on this section. So you want to find out how much force is being applied in a given area, and that will give you the pressure. So how do we calculate pressure? This calculation is what you need to know and memorize for calculating pressure. It's force, F, over area, A. Now force can also be measured in newtons, so you can also see N, but we'll just do force over area. Pressure, the unit of pressure is PA, and it stands for pascals. Right? And if you say kilopascal, kilo is Latin for 1,000. So kilo is 1,000 pascal. So a kilopascal is 1,000 pascals. This is denoted by kPa. Right? Now I'm not going to be too harsh on the capitalization if you just didn't capitalize the P, but if you are giving your answer in pressure, you need to give me the units. Right? You need to have that PA there. Or if you're doing it in kilopascals, you need to give me the kPa. If you don't, then it's going to affect you a little bit. So again, pressure can be calculated by the amount of force put on an area, and that is the pressure, and pressure is measured in pascals. So what is force? Well, force is the energy being applied, right? This person's applying a force on this wall, unsuccessfully moving it, but he's applying a force. And this force is called newtons. And again, the unit for newtons is N. So the force is applied in a unit called newtons. Calculate the pressure produced by a force of 800 newtons acting on an area of 2 meters. Right? So again, we know that F, force, over area equals pascals or pressure, right? So what is our force? 800. So I'll switch to a little bit quicker. 800, right? We have 800. And I'll draw a line, right? That's our 800 newtons over 2. Now, what you want to make sure you do is you give me the units, right? 800 what? Newtons. To what? Centimeters, or sorry, meters. And then you can put the little 2 up there. Meters squared. Right? So it's 800 newtons over 2 meters. Well then, 800 divided by 2 is 400. So you have a pressure of 400 what? PA. Never forget your units. I sometimes do myself, but for questions on tests and assignments, make sure you apply your units because I won't know what you're talking about, and so I don't know if you mean centimeters, meters, milliliters, and so on. So make sure you add your units. This question's a little bit different, right? This one's asking how much force is being applied if a woman standing on one foot puts pressure of 16 pascals over an area of 0.6 meters. Okay, well, now we look at our equation again, which is F over A, force over area. But we are looking for force. We are looking for the amount of force being applied, right? We have pressure. We have area. How can we find the force? Well, if you recall in our density lesson, we made a triangle regarding density, not density, density. We can do the same thing here, right? So force, so we put force on top, You know, I'm going to make this a bit bigger. Let's see, where's my eraser? There we go. Make this a bit bigger so it's easier to see. There we go. It's a little crooked, but that's okay. So we have F for force, right? Our force over our area, so A for area, right, gives us our pressure. And I'm just going to put P for pressure rather than the unit, right? So just like with our density triangle for our calculation for density, we can calculate force by getting the area and multiplying it by our pressure. And let's say we were looking for area. Well, then we would take our force and divide it by pressure. So in this case scenario, we're looking for force, and we have area and pressure. So it's A times P. Well, what's our A? 0.6, right? So we have 0.6 meters, and then we have to do that stupid little, there we go, times 16, right? So let's pull up our little calculator here. We go 0.6 times 16, 9.6. So, and that should be PA, equals 9.6 PA, or sorry, newtons. Right? I have my calculation. It's correct because, again, we follow this triangle. We have area and pressure, so A times P gives us F. So we have our newtons. 9.6 newtons of force are applied. When you apply a force on a substance in all directions, you are trying to compress it. This is what compression is, right? This is what compression is. When you apply a force on all sides of an object or a substance, you are reducing its volume using pressure, right? So if I have a square and I apply a force on every side, right? And I squish it down to a smaller square, or rectangle, then I have reduced its volume using pressure. Now, there's really only one state of matter that is very compressible. And you need to know this, unfortunately. You need to know that gases are the most compressible because of the high degree of space between the molecules. There's a massive amount of space between the molecules, which means you can apply pressure here, and here, oops, sorry, there you go, and here, and the molecules will get closer and closer together. Now, solids can be compressed, some can be, but not all. All gases can be compressed in some way. All solids, not so much. Only certain types of solids can be compressed, such as wood. But iron, oh, iron can with enough pressure, but other types of solids can't be compressed. And that's because if you look at the molecules, they're so close together. They're so close together. They are stuck together already, and they can't get any closer. So they can't be compressed. Liquids are a weird matter. With liquids, so if this was solids, we'll put S for solids, liquids, and gas, right? Oops, sorry, gas. Liquids are weird. When you apply a force in all directions on a liquid, it applies a force in all directions equal to that force. So if I were to put, let's say, 10 newtons of force in all directions, that's an N, there we go, that's an N, 10 newtons of force in all directions, the liquid pushes back with 10 newtons of force in all directions. So nothing happens. So it can't be compressed. Gases can be compressed. Solids and liquids usually cannot be compressed. And again, some solids can, liquids can't. That's because the molecules are already close together, right? They can't be compressed because the molecules are already close together. So we say liquids and solids that can't be compressed are incompressible. They are incompressible because they cannot be compressed. Gases can be compressed. So the gas in our air also creates a pressure all around us. We call this pressure atmospheric pressure. We call this pressure atmospheric pressure. This pressure is highest on the ground and gets lighter as you go up. So let's say we were standing right here. right here at the ground because we don't fly, right? Okay, well, the pressure we feel is all the air above us pushing down. That's the pressure we feel. And as you go up, well, if you were, let's say, on a mountaintop up here, well, there's less pressure because there's less air up here, right? Most of the air is down here. There's less air up here, which means that there's less pressure pushing down on you. And that's it. So where would we see compression in our daily lives? As gases are compressed, they push back in all directions. This counterforce has many uses, right? So similar to liquids, when you start to compress a gas really tight, it will start to push back. Liquids will basically immediately push back, but gases will start to push back after a certain point. So they'll get compressed and then start to push back. Well, tires are a key example of how pressure and compression can be used, right? As the mass of the car rides on the tire, the whole 2 tons of the car rides on these 4 tires. Well, the gas trapped in the tire pushes in all directions, right? Pushes in all directions. So pressure from the car, the 2 tons of pressure applied to the wheels, is then applied to the gas, the air in the tire, and that energy, that pressure, that force is pushed out in all directions. And that makes the tire very good at holding weight because it spreads that weight out in all directions. So the gas absorbs the forces of the car because, again, as the gas gets pressurized, as the gas in the tire is, as more pressure is applied to the gas, it pushes out in all directions. So there's some advanced uses of pressure you can see on your own time, but we're going to keep moving forward. Unequal pressures. So have you ever sucked on an empty water bottle? What happens? Well, what happens is, as you suck the air out of the water bottle, you are dropping the pressure. There's not as much air as there is on the, not as much air inside the bottle as there is outside the bottle. So now you have this super low pressure, this very low pressure, and this very high pressure. Well, pressure likes to move from high to low. So all that air is going to push onto this water bottle. And eventually, as you suck on the empty water bottle, that pressure is so high, it collapses. It collapses the water bottle, right? The pressure outside, so as you suck on the air, as you suck the air out, you are dropping the pressure in the bottle. The pressure outside is now bigger than the pressure inside and pushes on the bottle. The plastic then collapses because of the pressure, right? The pressure is high here, pressure is low here because you've sucked all the air out. There's not as much force pushing out from inside the bottle. So the pressure outside is pushing in, crushing the bottle. The air is crushing the bottle because pressure wants to move from high to low. Pressure wants to move from high to low. So if you have an unequal amount of pressure, pressure is going to try and equalize by moving from high to low. So our ears, have your ears ever popped on an airplane? Well, this happens because of pressure. As you move higher, pressure drops outside your body, right? And we go back to this picture. When you're high up in an airplane, pressure is really low up there. So what happens is the pressure inside your body is the same as ground level, and the pressure outside your body is really low because of, well, you're up in the air. So the high pressure inside pushes out, and it can cause your eardrums to pop, creating that popping feeling or that popping pain for some people as the pressure tries to equalize, as the pressure inside and the pressure outside are trying to be the same. The last slide is, how do we measure pressure? What makes pressure, how do we make pressure measurable? Well, what is used to measure pressure is something called a barometer. You need to know what a barometer is. It's a bit tricky. It's kind of like how a straw works. You take basically a tube. This is how old barometers work. You took a tube, an empty tube with nothing in it, or you try and empty out as much as you can, and you put it in an amount of mercury. Well, the air pressure from the outside, you have this higher air pressure outside and this low pressure inside. Well, now the high pressure wants to get in. It pushes on the mercury, which is a liquid, which then has nowhere to go except into the tube, right? It can't go this way because it's contained. It can't go this way because it's contained. It's got to go up. So it's going to go up equal to the amount of pressure in the air. So you can measure air pressure because the air will push the liquid into the tube equal to its pressure. Barometers are very good at measuring weather and for predicting weather because changes in air pressure change the weather, can cause the rain, can cause snow, hail, high winds, low winds, etc. So the application of pressure in everyday life is super important for understanding weather, for understanding how cars work, for understanding why our ears pop. And so pressure is applied every day in our lives. So for this lesson, you need to know what pressure is. Pressure is force over area, force applied over an area. You need to know the units of pressure and its calculation. Force is measured in newtons. Area can be meters. It's usually meters. And pressure is pascals. You also need to know kilopascals is 1,000 pascals. Force is applied in newtons or measured in newtons. Right? This triangle will absolutely help you. Please know it. Right? Force over area gives you pressure. Force over pressure gives you area. Area times pressure gives you force. Compression is the act of applying pressure in all directions to reduce volume. So it's the act of reducing volume using pressure. And the one state of matter that's usually compressible are gases. And that is because the space between the molecules is very, very high. You need to know that liquids and solids that can't be compressed are called incompressible. Incompressible. You need to know that atmospheric pressure is the pressure we feel on ground level. And that pressure decreases the higher you go, right? So an example would be Calgary is a very high city. The elevation of Calgary is higher up than, for example, Toronto. So the pressure we feel is less, the air pressure we feel is less than those in Toronto, than that of Toronto, right? Applying pressure. You should know at least one example, and the tire is probably the best one, of how pressure is applied in daily life. You could also use the ear popping or the barometer as application of pressure, understanding how barometers work, and understanding how it's used to predict the weather. You need to know how unequal pressures affect things. You need to know that pressure moves from high pressure, to low pressure. They want to be equal, right? If it has a pressure of, let's say, 10, and a pressure of 5 here on this side, right? Pressure is going to move, or whatever's making this pressure happen is going to move to this side, trying to make it equal. Pressure moves from high to low. And it'll try and basically collapse anything that is in its way. For example, when you suck the air out of an empty water bottle. The pressure outside is now higher than the pressure inside, and the air is basically ramming itself into the water bottle to equalize that pressure, causing the bottle to collapse. You kind of need to know how ear popping works, just based on how pressure is trying to equalize, right? In an airplane, it's very low pressure outside, very high pressure inside, and that pressure is trying to equalize. You need to know how a barometer works, that this tube is a vacuum or has very little material in it, and so the air pressure is trying to equalize from high to low inside the tube is low. And so a liquid, old barometers used mercury, would be pushed by the air pressure into the tube, and that measurement would give us the pressure of the liquid of the air. And that could be used for predicting weather. Sorry about that. So hopefully that was a useful lesson. I'll see you next lesson.